Hey guys, so we've spent a lot of time talking about intramolecular forces, the types of forces that hold molecules together, so the different bonds that we have, permanent bonds. So today we want to talk about intermolecular forces. We typically abbreviate these IMFs. Okay? So these are the forces that hold different molecules together. And when I say different molecules, I mean two separate molecules. It could be the same thing. So it could hold two water molecules together, for example. Okay, so it holds the two separate molecules together, but not the actual hydrogen and oxygen atoms within the molecule together. So these are temporary in nature. Okay, whereas the bonds are more permanent. These are very short-lived, and they're therefore weaker. Okay, so one thing before we get started, you'll hear the term van der Waals or van der Waal interactions used from time to time. That's just an older term to describe what we're going to talk about. So if you hear that in the future, don't be hung up on that. They're just types of intermolecular forces we'll be discussing. Okay. So there are three major types of intermolecular forces, or IMFs. The first one we want to look at we call hydrogen bonding. Okay, so we are fairly familiar with that, hopefully from biology. You've discussed hydrogen bonding before. Okay, in order for hydrogen bonding to be observed in a molecule between different molecules, a hydrogen must be bonded to a nitrogen, an oxygen, or a fluorine. Okay, so just because there is a hydrogen in the molecule does not mean you will observe hydrogen bonding. Okay, the hydrogen must be bonded to a nitrogen, an oxygen, or a fluorine. So let's look at the most common example of hydrogen bonding, which is the attraction between two water molecules. Okay, so if I draw out two waters, there are two lone pairs on the central atom when I draw my Lewis structure. So then I'll just draw another water up here. So those are my two molecules. We know these are covalent bonds that hold the oxygen and hydrogen together. What we want to look at today are the forces that hold the two molecules together, what keeps them bound together and prevents them from just flying away and evaporating. Okay. So before we look at these two specific molecules, let's look at another molecule of water. I'll draw down here. Okay. So I'll draw the lone pairs. So then, let me grab another colored pen. If I think about what makes up this covalent bond here, I know this bond is really just a pair of electrons that's being shared, because every single covalent bond is just made up by a pair of electrons. So if they're being shared, they're moving back and forth, okay, between the hydrogen and oxygen. Okay, they're being shared by those two, but they don't share equally, okay, because this is a polar covalent bond. Okay, we know that because if we look at the electronegativities of oxygen and hydrogen, they are very different. Okay, so oxygen is very more electronegative than is hydrogen. Therefore, oxygen attracts the electrons more than does hydrogen. Okay, so if we think about the electron moving back and forth, it's going to spend a lot more time around oxygen than it does hydrogen. Okay, because oxygen can better attract it. So if it spends a lot more time around oxygen, that means oxygen will have a slightly negative charge, and hydrogen will have a slightly positive charge. Okay, that's just due to their differences in electronegativities. So the same thing would be true over here. Oxygen is slightly negative, hydrogen is slightly positive, and also oxygen is slightly negative because it does have these lone pairs of electrons already on it, okay, in addition to the electrons being shared. And hydrogen doesn't have any lone pair electrons. It only has the electrons being shared in the single bond there. Okay? So if I come back and look at this example up here, we know that these oxygens will be slightly negative, okay, because of what I just discussed, and the hydrogens will be slightly positive because of what I just discussed. So something slightly negative is attracted to something slightly positive. Okay? So we draw that attraction with these little dashed lines like this. Okay? So this shows that there is an attraction, but it's not a permanent bond. And the hydrogen and oxygen are just holding each other together. Okay, they're attracted to each other. Okay, so they're creating this temporary and very weak bond or attraction between the two molecules. Okay, so we think about why this is important. Okay, intermolecular forces are what determine the boiling point and melting point of compounds. Okay, so the stronger the intermolecular forces, the greater the boiling point and melting point. Okay, so if you think about this as liquid water, in order for this water to evaporate, these hydrogen bonds have to be broken. Okay, so it requires more energy, okay, to break hydrogen bonds than it would to break some excuse me, weaker type of intermolecular force. Okay, so I could also draw this out between any other, or excuse me, many other types of molecules that have a hydrogen bonded to a nitrogen, oxygen, or fluorine. So if I think about another type of intermolecular force, the next type we'll discuss are dipole-dipole interactions. Okay, so hydrogen bonds or hydrogen bonding is actually a subset of dipole-dipole interactions. They're just a very strong class of dipole-dipole interactions. So dipole-dipole interactions are the exact same thing as hydrogen bonding. They're just not quite as strong. Okay, so if I think about a molecule, let's just say somewhere in a molecule I have a carbon bonded to a fluorine, and I have several of these, okay, and whatever the larger molecules might be. If I think about this covalent bond, I know it is a polar covalent bond because fluorine is far more electronegative than carbon, and it therefore attracts the electron density away from the carbon. Okay, so I have a slightly negative charge on the fluorines and a slightly positive charge on the carbons. Okay, so if I have a slightly negative and slightly positive charge there, and let me back up, I didn't draw the lone pairs of electrons on the fluorine. Depending on what the structure was, there would be lone pairs of electrons present there, but that's kind of beside the point. So I have a slightly negative charge here and a slightly negative charge here, a slightly positive charge here, slightly positive charge here. I see the same kind of situation. Okay? I have these very weak interactions form. We call these the dipole-dipole forces, or the dipole-dipole interactions, because fluorine has a slightly negative dipole, carbon has a slightly positive dipole. Okay, so you see it's the exact same thing that happened up here with hydrogen bonding, but it's just not specific to certain types of atoms being connected. Okay, so hydrogen bonding is just a special type of dipole-dipole interaction that only occurs when a hydrogen is bonded to a nitrogen, an oxygen, or a fluorine. Okay, so if we think about, again, why this matters, if you have a compound that exhibits only dipole-dipole interactions, then you have another compound that has hydrogen bonding. Because the hydrogen bonds are stronger than the dipole-dipole interactions, it will require more energy to break the hydrogen bonds to allow this specific compound to evaporate. Therefore, the molecule that has hydrogen bonding would have a higher boiling point and melting point than the molecule which just has dipole-dipole interactions. Okay? So the example written out in the notes would be, it says two molecules of acetone. So let's draw an acetone for the dipole-dipole interaction or dipole-dipole force. So acetone looks like this. So if you go through and check the electronegativities of this molecule and all its atoms, you'll see that oxygen is the most electronegative. Okay, carbon and hydrogen are very similar. Okay, so there won't be a significant dipole formed between carbon and hydrogen. However, with carbon and oxygen, oxygen will have a slightly negative charge, carbon will have a slightly positive charge. Then you on your own can draw another molecule of acetone and try and figure out how it will line up with this one and where you'll see the dipole interactions occur. Okay? So then the last type of intermolecular force that we see is by far the least significant and by far the weakest. Okay, and actually all molecules exhibit this force. Okay, we call them London dispersion forces. We'll abbreviate these quite often as LDFs. Okay, so if every single molecule has them, they're probably not super important, right? They're the least significant, so we don't discuss them a whole lot. But let's talk about why they occur for a second. So if I take CH4, for example, and I ask you to discuss the intermolecular forces present here, first ask yourself, do I have a hydrogen bonded to a nitrogen, oxygen, or fluorine? No, I do not. Okay, so I don't have any hydrogen bonding going on. Then do I have any dipoles? Do I have two atoms bonded together that have different or significantly different electronegativities? The answer is no. If you go check the electronegativity table, you'll see carbon and hydrogen are very similar, so I have no dipoles here. Okay? But I still have what we call London dispersion forces, because if I look at this bond right here, it's still made up of two electrons. Okay? The electrons are being shared between carbon and hydrogen. Okay? So if the electron's being shared, sometimes it's beside hydrogen, okay? Then sometimes it's beside carbon. Okay? At different moments in time, if the electron is present around the hydrogen, hydrogen might have a very temporary, slightly negative charge. Okay? Then instants later, when the electron moves to carbon, that slightly negative charge goes away and it adopts a slightly positive charge. Okay? Very, very small slight charges, and they are very, very temporary. Okay? They come and go very quickly. But anytime you have electrons moving back and forth, you're going to have the temporary or momentary slightly negative and slightly positive charges. Okay? And this is the reason this is how London dispersion forces occur. They are just the attractions between the temporary negative and the temporary positive molecules or atoms in the molecule. Okay, so at any given time, the forces would be constantly changing back and forth. The attractions will be changing back and forth because sometimes the hydrogen is slightly negative, sometimes it's slightly positive. Okay, so if I drew it out, we could draw it the same way, but we really don't care so much about diagramming this because every molecule has it. Okay, it's always present. So it's the same kind of thing as the two other types of forces. Okay, it's just what happens down here. The attraction with London dispersion forces are very weak and momentary, and they constantly change. The dipole-dipole interactions, or dipole-dipole forces, are kind of the same thing, but they aren't momentary. Okay, they don't flip back and forth. Oxygen is not sometimes negative, sometimes positive. Because it's more electronegative, it's always slightly positive. Okay, and the strongest we have hydrogen bonding. Okay, it is a greater attraction than any other type of dipole-dipole interaction that I have. Okay, so how we can apply this is if I ask you to rank or predict the melting points and boiling points of molecules. Okay, so let's stick with the three molecules we discussed already. So I have H2O, I have C3, H6O, then I have CH4. Okay, so I have water, acetone, and methane. So if I ask you to rank the boiling points, for example, okay, the molecule with the greatest intermolecular force or the strongest intermolecular force would have the highest melting point or boiling point, whatever I ask, because it requires the most energy to break the intermolecular forces. Okay, so because water has hydrogen bonding and hydrogen bonding is the strongest of the IMFs, it would require the most energy. Okay, then if I look at these two, okay, acetone and methane, because acetone has a dipole-dipole interaction, it would have a greater boiling point than would methane. Okay, methane would be the least because it exhibits only London dispersion forces. It has no greater attractions. Okay, so be aware of the three types of intermolecular forces. They'll come back up throughout the year, as well as when you study higher level chemistry, or especially biology, is where hydrogen bonding is most important. It comes up, and be able to rank the boiling points and or melting points of different molecules. And be sure when you see that question that basically you're being asked to describe the intermolecular forces present. Okay? Hope you have a good rest of your afternoon.